Real-world economic models are not static. Supply chains, currency markets, and corporate logistics are defined by continuous, compounding motion, where multiple variables interact simultaneously. Measuring the exact rate of change within these highly dynamic systems requires calculus. Specifically, it requires differentiation. This diagram demonstrates the standard mechanism you likely already know for basic polynomials. To find the derivative, you bring the power down to the front and subtract 1 from the exponent. X to the fourth power cleanly becomes 4x cubed. But this basic rule completely fails the moment variables act as exponents, become trapped inside logarithms, or multiply against each other. Look at these equations. These represent the types of interacting complexity we actually see in business mathematics. Our standard polynomial rules cannot solve them. To calculate rates of change in modern quantitative models, we have to define new base rules and build an advanced algorithmic toolkit to deconstruct composite functions. We begin with the first foundational component of our advanced models, the natural exponential function, written as e to the power of x. The letter e represents Euler's number, a constant approximately equal to 2.718 that naturally models continuous growth. The exponential function has a primary, unique property in calculus. It differentiates perfectly to itself. But look at this specific exponential equation. Here we have introduced an x coefficient, making the power 17x. When differentiating this, the rule dictates the power component absolutely does not change. Instead, the coefficient 17 drops to the front, giving us our exact derivative. dy over dx equals 17e to the 17x. Next, we transition to the second critical base rule required for business mathematics, natural logarithms, or ln. The fundamental derivative of the natural log of x is universally 1 over x. Notice the strict domain boundary here. X must be strictly greater than 0, because you cannot take the logarithm of a negative number. This raises a counterintuitive question. What happens to the derivative if that logarithm contains a coefficient, like 7x? Basic logarithmic rules let us split the constant away. The natural log of 7x becomes natural log of 7 plus natural log of x. Since natural log of 7 is a number, it differentiates to 0, leaving the derivative exactly 1 over x. Unlike basic polynomials, natural exponents and logarithms possess rigid inherent behaviors. Understanding these absolute invariants forms the bedrock of our advanced calculus toolkit. Now we address nested mathematical complexity. Often in advanced economics, an entire function is encapsulated deeply within another completely separate function. To solve this, we use the chain rule algorithm. The logic is sequential. We must first differentiate the outer layer, then differentiate the inner layer, and finally multiply the two separate derivatives together. Here is a typical nested equation. Y equals 2x plus 3, all raised to the power of 10. To keep the algebra manageable, we apply a strategic step. The inner expression, 2x plus 3, is isolated as u. This simplifies our main equation into an outer function of y equals u to the power of 10. Now we perform two distinct isolated derivations. The outer function differentiates to 10u to the 9th, while the inner function differentiates to simply 2. We execute the final step by multiplying those results together to get 20u to the 9th. Then we substitute our original inner expression back in, yielding a precise final answer. The chain rule allows us to safely unpack layers of mathematical complexity from the outside in without ever breaking algebraic laws. Next, we shift our focus to a different structural problem, equations where two completely independent functions are multiplied directly against each other. A very common pitfall here is assuming you can simply multiply their individual derivatives together. Mathematically, you cannot. Look at this equation. We conceptualize it by dividing it into two distinct functional blocks. X squared becomes our first block, u. The expression x to the 6 plus 9 becomes our second block, v. The product rule dictates a cross-multiplication approach. Multiply each original function by the derivative of the other, then add those results together. This gives our formal framework, u times dv over dx plus v times du over dx. We first calculate our isolated derivatives. The derivative of u is 2x, and v is 6x to the fifth. We complete the final assembly by dropping these pieces straight into our framework, mapping out the exact differentiated equation. The product rule ensures we accurately measure total systemic change when two distinct variables are concurrently influencing each other. We arrive at the final structural scenario in our composite toolkit, functions expressed as a fraction, where one expression is directly divided by another. Unlike the product rule, division introduces a rigid, non-negotiable order of operations. Order absolutely matters here. We take our target ratio equation and assign our variables. The numerator, x, is u. The denominator, 1 plus x, is v. The strict quotient rule follows a highly specific cadence. The bottom multiplied by the derivative of the top, minus the top multiplied by the derivative of the bottom, all placed over the bottom squared. This creates a complex master formula that governs all divided functions. By plugging our specific derived components into this framework, we generate the raw, unsimplified state of the derivative. From there, the numerator simplifies mathematically. The opposing x variables cancel out, leaving us with a clean, highly precise final derivative. The quotient rule allows us to isolate the exact rate of change, even when two continuous variables are inversely dependent on one another. At this stage, we pivot away from the mechanics of individual calculations and look at the broader philosophy of applied mathematics. Advanced calculus is not about memorizing infinite variations of equations. It is entirely about recognizing structural patterns. Look at this master structure. We align the visual pattern of the problem with the correct calculus rule. Nested functions route to the chain rule. Multiplied functions route to the product rule. Divided fractions route to the quotient rule. And those three composite rules are powered entirely by our invariant base rules for natural exponents and logarithms. By simply identifying the structure of a quantitative model, we can immediately route it through the exact algorithmic machine needed to deconstruct it. With this complete algebraic toolkit, you now possess the capability to derive the exact rate of change for nearly any complex, dynamic economic system in the real world.